Okay, let's keep talking about this relationship that we found here in the last video. So this was really a relationship that stated this F over A ratio is directly proportional to this delta L over L by a proportionality constant Y, which we called Young's modulus. And the important point on Young's modulus is that unlike K here for Hooke's law, Y does not care too much about the geometry and the composition of the material. Instead, it's looking at the relationship between this force being applied over this area and how that relates to the molecular bonds being stretched between each molecule. Now let's look closely at some of the terms in this relationship. So this F over A term you might know as pressure, and it is technically the same definition as pressure. However, in this relationship as it applies to materials or solids, this is known as tensile stress. So this F over A is for materials or solids. However, the F over A that we're familiar with, this is also known as pressure. But there are some very fundamental differences between these two definitions. Now, when we're talking about F over A or tensile stress for solids, understand that this stress is being applied in a particular direction. So in the case of this rod, this F was being applied along the length of this rod, whereas this F over A for fluids is pressure, and this force is being applied to all surfaces on that object or in all areas. So in other words, this tensile stress is being applied in a particular direction, whereas this pressure is being applied in all directions. Another difference is that this tensile stress has units of newtons over meters squared, and pressure is usually denoted in pascals, which again, fundamentally, those two are the same. However, the main difference is that pressure is being applied in all directions, whereas tensile stress is being applied in a single direction. Okay, cool. What about this delta L over L value? So this delta L over L value, in material land or solid land, we call this the material strain. And this strain is dimensionless, so it doesn't have a unit, because delta L is a unit of length and L is a unit of length. So those two dimensions or units cancel out, and this becomes a dimensionless term. So if F over A is our tensile stress and delta L over L is our strain, then we can rewrite this relationship between those two values in Young's modulus to be stress is equal to Young's modulus times the strain. And this is a pretty important relationship in materials or in objects. And so you'll have this Young's modulus, which is really stress over strain. So Young's modulus is stress over strain. Now, because this strain is dimensionless, it doesn't have units, Young's modulus takes on the same units that stress is. So in other words, Young's modulus is in units of newtons over meter squared. And kind of to put things into perspective, here are the Young's modulus of a few common materials. So we have steel, which has a Young's modulus of about 20 times 10 to the 10th Newton per meter squared. And then we have, let's say, aluminum, which has a Young's modulus of 7 times 10 to the 10th Newton per meter squared. And then finally, concrete, which has a Young's modulus of 3 times 10 to the 10th Newton per meter squared. So you can see that steel has a very high Young's modulus and concrete has a very low Young's modulus. Of course, this is all relative, so you can kind of very loosely think of the material, the softer the material, the lower the Young's modulus. And the harder and more stiff and rigid a material is, the higher the Young's modulus. Okay, and finally, now, if we look at this relationship right here, as well as the relationship of Hooke's law, we can actually rewrite this equation to solve for Young's modulus. So we can write this equation in terms of y being equal to something. So Young's modulus is equal to something. So if we take both of these relationships, and write them down here. So first we have Hooke's law, which is F is equal to K times delta L. And then we have F over A is equal to Young's modulus times delta L over L. Okay, cool. So if we take this second equation and I rewrite this slightly to where it's F over delta L is equal to Y times area over L, and all I did was divide both sides by delta L and then multiply both sides by A, and that's what got me this. And the reason I rewrote it this way is because this F over delta L is equal to K because of this relationship. Right? So if I take Hooke's law and I rewrite Hooke's law to be K is equal to F over delta L, then we can plug this in for this term here. So this equation down here really becomes K, which is our spring constant, is equal to Y, Young's modulus, times A over L. And if we solve this equation for Y, we get the Young's modulus is equal to K times L over A. And this is probably a more common relationship that you might see in textbooks or lectures. Okay, so far we've been studying these materials or these objects stretching. They're undergoing tensile behavior. So we have some sort of a force pulling on an object here, and then down here we went to study the more molecular behavior between this force and the actual material. All of this was in this linear region. So we're not looking at anything past the linear region here. All of this, Hooke's law as well as this definition of Young's modulus, applies within this linear region. And so for all of this, we've been studying how materials are stretched. Now, whether materials are stretched or compressed, this relationship of stress is equal to Young's modulus times strain is valid, so long as the material is in this linear region. Now, we can use what we've learned about this tensile stress behavior, and we can see how it relates to an object being subjected to pressure acting on all surfaces. So at the very kind of first part of this series of videos, I said that if you had some sort of an object that was submerged inside of a liquid, in this case water, this was a wooden block submerged in water, you know that there's going to be pressure inside of this liquid. And the deeper you go down, the higher that pressure. And the higher the pressure, the higher the force acting on all sides of this object. So really, as this block submerges down in this fluid, in this liquid, it's going to get compressed. And we can use this definition of stress is equal to Y times strain to figure out how much that object is going to compress by. And that was equal to our volume strain, which up here was defined as delta V over V. We are going to start that discussion on compression because all of this was on tensile behavior. Now we get to compress an object and see how all of this stuff that we've been studying relates to objects being submerged in fluids, or in this case liquids. But before we move on to that, let's do a few examples to kind of understand all the stuff that we've been learning in the last 2 or 3 videos. So I'll see you then.